Welcome to tutorial 4.3 part 2. This is on acids, bases, and their neutralization reactions. We'll talk a little bit about what an acid and base is and then write some neutralization reactions. So first of all, what's an acid? Acids are part of a class of compounds that play a central role in how chemists organize their understanding of substances. So it's just one of these kind of classifications of a central or important kind of substance. There's lots of different definitions, or several different definitions for what an acid is. The simplest one is what we're going to start off with, which is simply that an acid is something that increases the concentration of the hydrogen ions in a water environment. That is, when you dissolve something called an acid, you end up with more hydrogen ions in the solution than you had previously. They have a particular property that's historically of relevance. In the lab, of course, we wouldn't test this, but they tend to have a sour taste. So you associate them with things like lemon juice, citric acid, or things like vinegar, the acetic acid in vinegar. So first of all, what do we need to know about acids? They ionize in water. So here's an example. An acid like hydrochloric acid, HCl, ionizes in water to form those hydrogen ions. That's where those extra hydrogen ions come from. So how do we write this ionization, this turning into an ion? We say, well, the hydrogen chloride molecule starts off as a gas at room temperature, then when placed in a water environment, gets split apart into a hydrogen ion and into a chloride ion. And since that hydrogen ion didn't exist before in the water environment, we've increased the number of hydrogen ions and giving it therefore certain properties, the acidic solution. There's a little problem here. This is a convenient way to write this ionization, but it's a little bit misleading because it makes it look like this hydrogen ion, which is simply just a proton, is actually the thing that's existing in this water environment. And that's really not quite the case. The proton is actually attached to a water molecule. So to show it in a less misleading way, here's how we would write it. So HCl is a gas, meets up with a water molecule, and the proton gets transferred from the hydrogen chloride molecule to the water to form the hydronium ion and chloride. So this is a better way to write things when you're trying to be clear, but in terms of the bookkeeping, this is actually a little bit more cumbersome. So I'm going to keep showing you this way of writing it, but this is the top way, is what we're going to really focus on, because it's easier for students, especially at the beginning. All right, so let's look at a few of these ionization reactions that kind of make sense of what's happening. How do we imagine this event taking place? The hydrogen chloride in the presence of water getting split apart. So here I'm just showing a hydrogen chloride molecule. I've drawn it in a different orientation. First, the hydrogen to the right, so you can imagine it getting pulled over to this water molecule. And this little red dot here is supposed to represent one of the shared electrons, and the electron that originally came with the hydrogen. That's how we're thinking of it. And that's the thing that's going to get left behind. As this hydrogen gets pulled over to the other side, it's not the entire, the electron that it was initially part of the atom that comes with it, but just the proton. So this thing approaches the water, and what happens? All of a sudden, this proton has a choice. Do I stay with the chloride, or do I go over to the water side? And it turns out it's going to be more attracted to the water side than over to the chloride side. So what happens? It jumps ship and ends up as part of the water molecule. And this is the hydronium ion that's now in the solution, and that's the chloride ion. And it's this thing that we're actually representing just with that H+, as if it were sitting by itself, surrounded by water molecules. Now here's the equation finally written out. Hydrogen chloride in the gas phase is in a water environment, meets up with a H2O molecule, and the proton, this proton jumps ship, goes over to the water, and becomes the hydronium ion, and the chloride ion is now free to be surrounded by the positive end of some water molecules, and therefore is in solution as an aqueous compound. All right, so let's try a couple more of these acids. So here's nitric acid, HNO3. The exact same thing. The molecule just looks a little bit more complicated because this nitrate unit, the 3 O's surrounding the nitrogens, are more complicated looking. But apart from that, it's exactly the same thing. In red, again, I've tried to show the electron that initially was part of this hydrogen atom before it was bonded to this group. Again, it's attracted over here to the water molecule. And so it's over making a decision, do I go to the left or go to the right with the water? Turns out it's going to go to the right and actually become part of the water molecule as the hydronium ion forms. That's this ion. And notice the plus charge, I didn't emphasize that before, just the proton came over. It didn't bring its electron, and therefore it has a positive charge. Therefore, this NO3 group called nitrate now has a negative charge. It has that extra red dot, that extra electron that used to be making, the thing was neutral before, but now it has a negative charge because the electron was left behind by the transfer of this proton. How do we write it? As before, the nitric acid molecule, liquid at room temperature, meets up with a water molecule. The proton jumps over to the water to form the hydronium ion, and the nitrate is what's left over in the solution. All right, so let's look at a different one. So now all of a sudden things have changed slightly, and they look a little more complicated. I have over here this double arrow, and that's supposed to be indicating that the reaction can go forward and in reverse direction. So that's kind of a new thing. But apart from that, it looks pretty similar. But then you also have a little bit, perhaps a little bit of an issue, like, what's with these hydrogens here in the middle? Why didn't I put all four hydrogens together? And it's because it's this hydrogen that is acidic. It's this hydrogen that can be pulled off of the molecule, not these. These hydrogens are pretty stable. They're not going to be removed by the action of water. Okay, so notice the orientation again. It's this proton that gets pulled off to the water. These hydrogens over here are stably are bonded to this carbon. They will not be removed by the action of water. So it's only this one that gets pulled over. Here, this part looks the same. We've got this tug of war going on. The hydrogen ion, the proton, if it could talk, should I stay with the acetate or should I go over to the water? It goes over to the water some of the times, but it actually is going to be happier to stay and remain part of the acetic acid molecule most of the time. I've got this arrow here, this new arrow, to show that, this thing could form, but it could reform again. This hydronium ion, if it ran into this acetate ion, could reform again to form the intact acetic acid molecule. Hence, this kind of double arrow that we're showing here, that this is not a one-way thing, that you lose the proton, it's lost forever. Instead, this is kind of back and forth. So this is called a weak acid instead of a strong acid. It's a more complicated situation because of this kind of equilibrium that gets established between the acetate ion and the acetic acid molecule. We'll look at this again later, but for now, let's just kind of keep going. One other thing to notice, though, is that this particular group here, this C double bond OOH group, is an indicator for the most part that we're dealing with weak acids, that acids like acetic acid that I just showed you. It has a special name. It's called a carboxyl group. So if you're asked and you see some kind of molecule and you see the C double bond OOH and you're asked is this a strong or a weak acid, you're going to say, oh, it's a weak acid, I suspect, like the particular example given, acetic acid. So notice over here, there's also a little issue with how to write this thing. If you want to emphasize that you've got a carboxyl group at hand, this way of writing it, the initial way I wrote it, is actually not very helpful. This is helpful only in that the hydrogen in the front is shown, that you say, oh, that's the one that's going to be removed by the water. So that part makes this way of writing easier to see. But it doesn't actually show that you've got one of these carboxyl groups. So to indicate that, often you'll see it written like this. This is the same thing. Notice there's 2 carbons here, 3 hydrogens, the 2 oxygens, and this acidic hydrogen off to the side. But the way it's kind of written is different. I like this way of writing it at first for students because they clearly see there's a single hydrogen that's going to be donated. But this way here shows you a little bit more of the structure. It shows that carboxyl group. It indicates the same thing. So notice these two indicate the same stuff. Now this is the acetate ion and so is this. They're just written in a slightly different way. All right, how do you write this then? If you want to show the water molecule that's doing the removing of the actual proton, we write it in this way. That's the familiar way. Or if you write the acetic acid molecule to show its structure, it's the same thing. It's just that this is the proton that's going to be removed to make the acetate ion. I hope that made sense. Slight digression here. So here's another thing that comes up with acids. Sometimes a particular molecule has more than one hydrogen that can be removed. We noticed with acetic acid there was only one, but what happens if it's possible that you can have a second one that's removed? That happens, for example, in sulfuric acid. So here's sulfuric acid. The first part is the same as we've seen before. We remove a proton, we end up with the hydrogen sulfate ion, But then what happens, that hydrogen sulfate ion itself can have that proton removed. So we get another hydrogen ion, and finally the sulfate ion is floating off by itself. Now this one here, this first hydrogen, is removed essentially from every molecule that dissolves in water. But this hydrogen here is actually not so easy to remove. So this hydrogen sulfate is actually a weak acid. It's the sulfuric acid, that is the loss of that first proton, that makes the sulfuric acid a strong acid. So if you wanted to show the entire thing at once, we'd say, okay, sulfuric acid forms two hydrogen ions and a sulfate, but remember, we're actually in a solution of sulfuric acid going to have some hydrogen sulfate ions floating around and some hydrogen ions, or the hydronium ion, and some sulfate ions. So all of those are going to exist at the same time. So here's a few pictures to kind of show this to make sure it's clear. This hydrogen is the one that's going to be the easiest to remove. If it's the one on the left or on the right, they're symmetrical, so it wouldn't matter. But one of the two is easy to remove. But once it has been removed, and we have the hydrogen sulfate ion, the second one's not so easy to move. So this substance, the hydrogen sulfate, is a weak acid, but the original molecule is a strong acid. So once we've removed both of them, we now have a double negative charge because we've lost two protons. So notice, this is different. We had before in the acetic acid molecule extra hydrogens that were not removed. That's a different situation than this one here, where we actually have a diprotic acid. Two protons can be removed, but the first one is the one that's easy, the second not so easy. All right, so that's a little complication. It really only comes up with sulfuric acid for us. There's some weak acids like carbonic and phosphoric acid where it's prevalent as well, but they're weak acids to begin with, so they're not quite as confusing as the sulfuric acid example. All right, quick summary of what we've looked at so far. We've got hydrochloric acid that splits apart. We've got nitric acid that splits apart. Acetic acid, double arrows, because the split is not a one-way street. It also can go back and reform. It's going to predominantly exist in the solution as the acetic acid molecule, with a little bit of hydrogen and acetate ions floating around. Here's just a different way of writing the same thing. And then finally, the most complicated one, the diprotic acid, sulfuric acid. Yes, it's a one-way street to remove the initial proton, but a two-way street when it comes to removing the second proton from the hydrogen sulfate ion. When written as a intact molecule H2SO4, we could write it this way to show that both hydrogen ions are removed from the sulfuric acid molecule. All right, that's it for acids. Now let's have a look at bases. So what are bases? Acids can be neutralized with a class of compounds called bases. It's the first easy way to think about them. There's different definitions again for bases like there are for acids, and the one we want to use is the one that says that a base is a substance that actually increases the concentration of hydroxide ions when dissolved in water rather than hydrogen ions. Now this might seem slightly a little bit like an odd definition. You say, well, I'm not quite sure why hydroxides now that we're using as a definition for bases, but remember, when you have a hydroxide ion that meets up with a hydrogen ion in a water environment, they will neutralize each other. That is, they're going to turn into a water molecule. So it's in that sense that it also makes sense. And you'll see by way of some examples why this is a reasonable definition. What's the property? The way we said that acids were sour. The big property for bases is that they are bitter and they feel slippery. Again, don't taste them obviously in the lab, but sometimes you'll notice if you get a little bit of a slight amount of base on this outside of a beaker, that the beaker will kind of tend to be a little bit slippery. All right, so what are some common bases? So first of all, the soluble hydroxides, and that would be all the alkali metals with hydroxide are soluble. And there's a few others as well. You'll see down here in the hydroxides we have calcium, strontium, and barium. Those alkaline earth metals are also soluble, at least partially. So they are also designated as common bases that are strong bases. So here's a dissociation for these. Sodium hydroxide turns into the sodium ion and hydroxide ions in solution. That's just how they dissolve. Same with potassium hydroxide and the same with calcium hydroxide. There are also some weak bases. The weak bases are slightly confusing. You're over there looking for a substance that can create a hydroxide ion in a solution, and you're told that ammonia, for example, NH3, is a weak base. And you're like, where's the OH group? I don't know if this thing is supposed to be producing a hydroxide ion in a solution that can then neutralize the hydrogen ion from an acid. Where's the OH? I don't see the OH. Another example here is this ethylamine C2H5 with the NH2 group, and those are bases. And the reason that that's confusing is you don't see the hydroxide. So where does the hydroxide come from? They come from the water molecule that they react with. So what happens is you end up placing one of these in water, and the water molecule gets pulled apart. It doesn't happen that readily, though, so therefore we call it a weak base, because not all of the molecules are going to actually be able to pull apart water molecules to form hydroxides. So you don't get as many hydroxides per molecule as you do with the strong bases. Here's the reaction. This NH3 molecule meets up with the water. The hydrogen gets pulled off onto the NH3 molecule to form the ammonium ion NH4+, and then the hydroxide's left over. It initially was part of the water molecule itself. So that's what gives it these kind of the properties that we associate with bases, being slippery, being bitter, and being able to neutralize acids. The same for the ethylamine. What happens here is the hydrogen gets pulled off of the water molecule to form this NH3+ grouping as part of this kind of ethyl group, and then the hydroxide is off by itself. Okay, so those are a little bit easy to get confused about, but hopefully that's all right. And we're running a little long time-wise. We're at 16 minutes, but let's run through now a few of the actual acid-base neutralization reactions, which hopefully, now that you understand a little more what acids and bases are, should be pretty straightforward. So first of all, what happens when you put acid with a base? Well, they're neutralized. They're going to be of this basic form, and this is going to remind you of a precipitation reaction. It's just this partner switch. The positive A can go with the negative Y. That's one possibility. And the B can go with the X. That's the other possibility. So what's different about this than precipitation reactions? Well, the thing that's forming on the other side is not an insoluble precipitate like we saw before, lead chloride or potassium, lead iodide, that kind of thing. Instead, it's going to usually be a water molecule that's forming, because the positive ion from the acid goes with the negative ion from the base, and they form some kind of they form water. That's the common thing. But it's also possible for other things to happen, like, for example, carbon dioxide, hydrogen sulfide, or sulfur dioxide might form in one of these neutralization reactions. All right, so let's have a look at some examples. First, just a little note. When you have a neutralization reaction between a metal hydroxide, you end up not only making water as one of the products, but something called salt. NaCl is the most common salt, but the other products of any of these neutralizations is also referred to as a salt. All right, let's look at a few examples. Hydrochloric acid and sodium hydroxide, and the sodium hydroxide is in the dissolved state. So first of all, I've highlighted in red what's going to happen. The hydrogen ion from the hydrochloric acid solution meets the hydroxide ion to make a water molecule, and we end up therefore having the acid with the base turning into water plus a salt. Let's look at another one. This time what's different is that I left the sodium hydroxide as a solid, so imagine a group of solid material sitting in a beaker or something. As you pour the hydrochloric acid onto the solid, again the same reaction takes place, but in the process the sodium hydroxide is actually dissolving, but it's the same thing apart in terms of the way you balance the equation, etc. Again, acid plus base goes to water and salt, and of course we're neutralizing the acid as this happens. Notice this next one, and this is a nice one to see. Magnesium hydroxide is not initially soluble, so you couldn't mix a solution of hydrochloric acid and magnesium hydroxide because it's insoluble, but you can certainly pour the acid onto the solid magnesium hydroxide, which then will neutralize it, and we'll end up with a solution of magnesium chloride. And it's nice to see this thing out in pictures. On the next slide, I'll show a few pictures of this. So let's kind of make sense of what's happening here. Here's some milk of magnesia, which is just some solid suspended in water of these magnesium hydroxide crystals. So what happens here with this thing? The magnesium hydroxide is insoluble, but in the presence of the hydrogen ion and the chloride ion, what's going to happen? These hydrogen ions are going to attack this thing and form water molecules, and that's going to release the magnesiums into the solution along with the chlorides that are already there. So let's see what happens here. So here's the hydrogen ions that are attacking this thing, and we're going to end up with these hydroxides, these kind of red-white combinations. They're going to get that extra hydrogen to form into these water molecules. Remember, the chlorides were there already to begin with in the hydrochloric acid solution, but now what happens to those magnesiums? Well, they're no longer part of this crystal, so they end up freely floating independently, and you can see them over here. As a matter of fact, you're going to end up with, for every one magnesium, and we have 2 chlorides in there that came initially from that acid solution. The balancing helps you keep track of all that, and notice on the picture, the solution all clears up because all of the solid has reacted to form this new solution of magnesium chloride and water, and it's been neutralized. So why would you do this? Why would you drink this stuff? You have a stomach ache, and presumably the stomach ache is because you have an acidic stomach, and this is just going to neutralize the acids in your stomach. That's all that's going on there. All right, I think 1 or 2 more examples. Is going a little long. I apologize. We're at 20 minutes, but we're almost done. A hydrochloric acid in a solution of calcium hydroxide, same exact deal. Why am I putting it? Just because it's just not a 1-to-1 ratio for the hydroxide. So you end up making 2 water molecules over here for every calcium hydroxide unit. And then finally acetic acid to show a weak acid. Same exact thing happens. The hydrogen goes with the hydroxide to form water, calcium acetate. This might only throw you because you might say, well, wait a minute, I thought this thing was weak. Do I have as many hydrogen ions as I did before? And the answer is going to be yes, but the reasoning behind it is going to be a little more complicated than we want to deal with now. All right, I think that's it. Oh, one more example, barium hydroxide. I think we'll just throw it in there real fast with acetic acid. Same deal, hydrogen with the hydroxide makes the water molecule. I spoke too fast. I forgot about these slides. All right, so a couple more. Sometimes the neutralization does not involve hydrogen and hydroxide, but instead there might be a different substance that the hydrogen ion can react with. So here's an example of this kind of thing. What if you had a solution of sodium sulfide? No hydroxide ions here. So this doesn't quite fit our definition of the base that I gave before. I said, well, I don't know, is this thing going to be called the base? We're going to right now say, well, it's a base in a different sense of the word, of something that can accept the hydrogen ion to be neutralized. So it's considered an acid-base neutralization. It doesn't quite follow the pattern that we had before. So what happens here? The hydrogens meet up with the sulfides instead of with the hydroxide to form water. Instead of forming water, we make this gas, this kind of nasty smelling hydrogen sulfide gas. So that's a different kind of reaction. So notice this time we get a gas and a salt. There's also another type over here. This is the sodium carbonate that forms. Again, it doesn't quite follow the pattern. There's no hydroxide ion here. Instead, there's this carbonate ion that's in solution. It meets up with these hydrogens, and you make this H2CO3 to begin with, and that substance itself breaks down into H2O and CO2. So this one's the more complicated one. You've got this carbonate ion, and then you end up with the H2CO3 in solution that itself becomes water and CO2. So when you see this all at once, it's a little bit confusing because you can't quite tell where the extra material come from. You made both a water and a gas molecule. I think I do have one last one of this same sort. And what's the difference here? What if you had a hydrogen carbon ion to begin with? It would work the same way. Your reasoning would be hydrogen ion meets with the hydrogen carbon again, not a hydroxide. Again, once you see that you've made the H2CO3, just split them up and say, okay, that makes H2O and CO2 predominantly, and that's what that final reaction is. Whew. I think we finally did get to the end. I think that's the last one. Oh, I have one last one just to confuse us. A triprotic acid, just to make sure those don't throw you. So here's a H3PO4. Back to the nice easy ones where it's just hydroxides, and we make 3 water molecules. Okay, now that's got to be the end. I really went over here, 24 minutes. Oh, I'm in big trouble. Good luck with this. I went a little fast, despite the fact that we're at 23 minutes. We obviously need to practice this in class. We'll do it nice and slow. I think if anything that's going to throw you is the fact that not always is a hydroxide ion involved. Sometimes it's these sulfides, and it's the carbonates that seem to throw people, the hydrogen carbonate or the carbonate ions. But remember, you're always going to make H2CO3, which turns into H2O and CO2. And again, with practice, you'll get confidence. We'll be in good shape. All right, we will see you in class. Sorry we ran so late on this one.